Okay, so this first section is a continuation of section 4.2, applying congruence in triangles. Example 4, we're given that rectangle PQRS is cut in half by the segment PR, and we want to show that the halves are congruent to each other. So right now the only way we know to show that figures are congruent is to show that all the corresponding parts are congruent. So first of all, I know that angle S is congruent to angle Q because they're both right angles, and all right angles are congruent. It's a rectangle, so because of that, I know that PQ is actually parallel to SR, and I know that PS is also parallel to QR. And that's because opposite sides of a rectangle are parallel. Now, if I look at my figure, if I first look at PS and QR, and I consider PR my transversal, I have a set of alternate interior angles right here, angle 1 and 4. So because the lines are parallel, I know that angle 1 and 4 are congruent to each other. And then looking at the other lines as my parallel lines, looking here at PQ parallel to SR, again, PR is my transversal. This time my alternate interior angles are 2 and 3. So angle 2 would be congruent to angle 3. And both of those are congruent by the alternate interior angle theorem. Alright, so now I've shown all the angles are congruent, I have to show all the sides are congruent. Well, fortunately for us, they gave us that. And I know that PQ is congruent to SR, as that was given in the figure. Also, opposite sides of a rectangle are congruent. QR is congruent to PS, again given, or because opposite sides of a rectangle are congruent. And then finally, I haven't said all three sides of the triangle are congruent yet, and PR and RP are the same thing. The triangles are sharing a side, but I still have to say, even though it's obvious that something would be congruent to itself, you still have to state it. And so PR is congruent to RP by the reflexive property for congruence. Now the reason I switched the PR around, PR congruent to RP, is because in the second triangle, R is corresponding to P, and then P is corresponding to R, so they're actually reversed in the congruent statement. So I've said all 6 parts of those triangles are congruent. I can now say triangle PSR is congruent to triangle RQP. And that's because of the definition of congruent figures. Next, we're going to look at the third angle theorem. The third angle theorem states that if 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles are also congruent, which makes sense logically. They both have to add up to 180, so the part that's left over is going to be the same if the 2 pieces subtracted are the same. All right, so we know the way this would look in a proof is you would have to say that angle A is congruent to angle D, and you'd have to say angle B is congruent to angle E. In this case, that was given to us. And then after stating those things, I could then go on to say that angle C is congruent to angle F, and my reason would be the third angle theorem. Okay, so let's take a look down here at example 5. I've got a triangle over here, triangle STU, and I want to find the measure of angle V. Well, first I can find the measure of angle S because I have 2 out of 3 angles. I know that the measure of angle S plus 66 and 44 are going to have to add up to 180. And so if I combine my like terms, I get 110. I subtract that from 180 and I get that the measure of angle S is equal to 70. Well, if I look at what's given to me in the figure here, I can see that angle STU is congruent to angle VWU, and I know these two are congruent by vertical angles. So that means that angle S would have to be congruent to angle V by the third angle theorem. And so therefore the measure of angle B would have to be 70. Okay, and then the last little part of this is just saying that properties for congruent triangles, we can use reflexive, symmetric, and transitive for congruent triangles. So for any triangle ABC, triangle ABC is congruent to triangle ABC. It's just looking at itself in the mirror. It's the reflexive property. Symmetric means they can switch places. So if triangle ABC is congruent to triangle DEF, then triangle DEF would be congruent to triangle ABC. And then the transitive property, if ABC is congruent to DEF and DEF is congruent to JKL, I can say that triangle ABC is congruent to triangle JKL. That's the end of section 2. We're going to move on now to section 3 of chapter 4. Okay, so the lesson objective for section 4.3 is that students will prove triangles congruent by side-side-side congruence postulate. What the side-side-side congruence postulate says is if 3 sides of one triangle are congruent to 3 sides of a second triangle, then the 2 triangles are congruent. So in my figure here, I know that triangle ABC is congruent to triangle RST by side-side-side. So you don't have to actually write out side-side-side in a proof. You can just write SSS. All right, so looking at this example here, we want to know, is the congruence statement true? So if I look at example A, I've got JKL congruent to MKL. Well, if I was doing this as a proof, I would have to list all the congruent sides. So I can see that JL is congruent to ML because they have equal measures. And I can see that JK is congruent to MK because they also have equal measures. And then finally, I know by the reflexive property that LK would be congruent to LK. And so, yes, those are congruent by side-side-side. All right, so now if I look at example B, I can see that they gave me that ST was congruent to VW, and they also gave me that RT was congruent to TW, but they only gave me 2 sides. They didn't tell me anything about RS and TV, so there is not enough information. All right, so what's it look like when we use it in a proof? For this figure, we are given that FJ is congruent to HJ, and we're given that G is the midpoint of FH. And we're going to prove that the 2 triangles are congruent. So before I start, let's just talk about what I know. If G is the midpoint, then that means that it cuts it exactly in half, and those 2 segments have to be congruent. And I know that JG is going to be congruent to itself by the reflexive property. So I can see I have all 3 sets of sides that are congruent to each other, so that's basically what I have to say in my proof. So we start off with what we're given, and then because we have the midpoint, I know that FG is congruent to HG, because that's the definition of a midpoint. And next I would say that JG is congruent to itself, by the reflexive property for congruence. So now if I look at what I've got here, here's one side, here's the other side, and the third side. I've got all three sides listed, so by side, 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 I can say triangle FGJ is congruent to triangle HGJ. So when you're using side, 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 you need to list all three sides being congruent, and of course you have to have a reason for believing that, and then you're done. You can say the triangles are congruent. Okay, we can also use the distance formula to show that triangles are congruent. So I'm given triangle DFG, which is D is at -2, 4, F is at 4, 4, and G is at -2, 2. So there we have triangle DFG. And then my other triangle, LMN, L is at -3, -3, M is at -3, +3, and N is at -1, -3. Okay, so that's L, M, N. All right, well, they were nice to us on this one. They gave us the some of the lines right on there. I can see that DF is equal to 1, 2, 3, 4, 5, 6. And I see that ML is also equal to 6. So I know that DF is congruent to ML because they have the same side lengths. Then if I look at DG, it's all got a length of 2, and LN also has a length of 2. And so I know that DG is congruent to LN. All right, that's 2 of my sides. Now I just got to show the third sides are congruent. So if I look at GF using the distance formula, I'm going from a -2 to a +4, that's a distance of 6. And I'm going from a +2 to a +4, that's a distance of 2. So that's the square root of 36 plus 4, which is the square root of 40. And so GF would equal 2√10. And then if I do MN, my X is changing by 2, my Y is changing by 6. So I end up with 36 plus 4 again, well, the other order, which is the square root of 40, and that's also 2√10. So that means that I know that GF is also congruent to MN. And so after I've seen that all three sides are congruent, I can say triangle DFG is congruent to triangle LMN by side, side, side. So we can use congruent triangles to determine whether or not a real-world figure is stable. So if we look at this example here, if a real-world figure contains congruent triangles, then it'll be stable. So if I look at my two tables, the second table's legs make congruent triangles. And so that means that the second table is in fact stable. The first leg has lots of possible quadrilaterals, so basically it could be pushed and slanted over, so it is unstable. So if we look at another example down here, if I look at the first figure, it's a rectangle, and I can see that those sides are congruent, these sides are congruent, and of course this is congruent to itself. So yes, that one is stable because I have congruent triangles by side, side, side. But if I look at the second figure, there's no triangles at all, and so it actually could move a little bit, and this one would not be stable. All right, that concludes the video. Thank you.